begin. Okay, so thank you very much. I hope you are doing well, and maybe a few later on we can just chat briefly besides the points that we have here. But today I want us to look at something that you have used several times, and we'll be looking at the technology behind it. How it's set up. Discussion today is what we refer to how peer-to-peer technologies. Now, so the concept of peer-to-peer means equal in terms of capacity, maybe equal in terms of capabilities, equal in terms of what it can do. So when you're looking at peer-to-peer technologies in terms of when you're looking at peer-to-peer technologies, what you are simply saying is that we need to be able to use, design, or adopt technologies that help us to access or have more things being done as opposed to what you have discussed before. Now, this follows our discussion on client-server model. And so it's very, very important, first of all, to think of it that from a client-server concept, we have certain and server concept. So we shall be maybe mentioning some of those as we continue with today's discussion. So the first thing is a peer. So when you talk about a peer, they act as both suppliers and consumers of information. In our earlier discussion of client-server concept, we had a model whereby the server supplies the information that the clients consume. So this means that we have limitations, okay? We have just a few, maybe servers. Of course, servers are expensive, and they are the ones that are going to be able to provide the services that we require. Now, but so one makes a request, which is the client, and the server provides the service. Now, that has limitations, as I've mentioned. And so we are saying we want to look at a model that is such that it can be able to perform both the supply and the consumption, and it has advantages. So that's where we are saying that we end up now having a peer-to-peer. They're equal partners, okay? So they are connected, and they can be able to supply information to each other. They can be able to consume information from each other. This is now on top of what we know before. So instead of having just a client requesting a service, we now have a scenario where we have a client, we have a peer that is both a client and is a server. Okay, so we have, if we compare, CF means compare. If we compare what we had there, we are assuming that, okay, the server here has high capability, okay? It has high processing power. It will provide the services to the ones that have. So in this model, we are assuming someone can simply invest in, referred to in some cases as dumb terminals. Dumb terminals. The dumb terminals, basically, they don't have high processing power. Technologies we have, smartphones, laptop. They don't make much sense in this particular era to have totally on client server model. So we end up saying that basically this concept that we had earlier on, where the client requests information and the server is of data. Okay, and this it's the only. We are saying that this is no longer very attractive. We are not saying we are doing away with it, but we are saying that we have abilities that are available, that we don't have to rely on our model. So we are saying, therefore, that these clients here are no longer dumb terminal. And they might even have the same capability with these ones here, okay, the servers. And hence, we are saying the clients and the servers are peers. They have the same capabilities, okay? So that means that this, okay, it's possible that the client can also perform the same. To recap, why we need peers is that we are avoiding single point of failure. Okay, single point of failure. So let me go back on the previous diagram. Okay, just to recap. If you look at this diagram here, okay, if we have this as the only server, if it goes down, that is a single point of failure. It's a bottleneck to the distributed environment. It's a bottleneck to the distributed environment. And therefore, what we are saying is that we end up, we need a scenario where we do not have or we minimize single point of failure, okay? Which basically might require that the server will require administration. So, of course, like expected servers. And this one here means that it it can ensure that the other client's function is a bottleneck. That aspect of administration of the whichever functionality we are working with can be distributed. Okay, so some of the resources of clients cannot be used, so it's a wastage. Now, remember, this point here, I'm trying to refer to what I said earlier on. We have technologies that are now more powerful. Okay, your laptop is more powerful. It can actually be a server. Okay, your smartphone is powerful. It can be a server, and hence the need to be able to go to peer and peer kind of structure. Okay, and so some of these things that we are mentioning, therefore, as we discuss P2P technologies, we are saying that P2P technologies is addressing some of these limitations of client server models. So if we compare those two, okay, we'll have that the client server model will be something like this one here, and okay, whereby we have these as the clients, the requester service. Now, in the peer-to-peer model, you notice that we have arrows. Okay, let me use a different one. We have arrows. Okay, so we have arrows to indicate that each you can see this. If you look at it, some of the things we discussed before in terms of cumulative computing power. So this is what it's saying. So this has an opportunity to give us a cumulative computing power. Okay, so we can have all these ones now combined together to be able to provide. So, and this is some of the powers we have when we have, for example, down quickly. So that cumulative computing power, very, very good. This one, in this other part here, we have a single where is not good, because the moment you have a the moment you have a problem on this particular server, you so this figuratively is client to peer-to-peer versus client server model. Now, so this calls for looking at the architecture. Okay. This P2P. Okay. So usually ad hoc networks. Okay. They're usually ad hoc networks where addition and removal of nodes has no significant impact on the network. So you can add, okay, you can remove, okay, and this is distributed, which means that it can provide enhanced scalability and service robustness. What do I mean by that? Okay, so from robustness, let's look at it. The simplest is geographically. So it can go to a wide span. Okay, and robustness is an environment where you are saying that if there is any there is failure for any of the nodes, the distributed environment can easily be able to adjust and continue providing the services without the users noticing any degradation in terms of performance. So the peer-to-peer technologies utilize an application layer, which we call an network. Okay, so basically, and just on top of. Okay, so I will answer that question. Afanti, please, let's pick up that later on. So question later on, placed on top of the native physical layer. Native physical layer that you have, a native or physical network that you have at that particular point. And basically, it does not disrupt. And the way it behaves is simply sending a packet. I just append some information on top of that packet. Okay, so that packet will help me to we can use indexing to be able to allow us to do quick routing. So the peer-to-peer ad hoc networks run on top of the native office, and they are very good in terms of helping us to discover new peers. Why is that important? Because we have said it's ad hoc. So we keep on adding things, we can remove things. So adding provides, of course, potentially new services, and therefore we need to be able to discover those services and we can use them. So, so if you look at this slide, so the P2P application over the overlay network, you have the same networks here, but we're just running, we have exists with several, if you notice what we have here, these are several nodes that are communicating. So they're sending packets to each other. So the overlay network packet. You wanted to communicate from A to B. I attaching something on that particular network, and it goes along. So we are not setting up a new network. We're just having what we call piggybacking, whereby you have information that is just appended on top of what already is being conveyed among the different nodes. Okay, so the overlay networks here are just an overlay over the existing network to allow us to index and peer collection. The overlay network has no control of the physical network or any of the physical network. So it's not something that you're saying is going to take over the control of that network. No. Okay, and so in this case, therefore, we have a fairness in terms of resource sharing, okay, and resource coordination, because it does not take over that particular network. So it decouples the network services of the underlying infrastructure by encapsulating packets inside another packet. Remember the concept of encapsulation. Means I just add something. Okay, sorry. Let me use a clear, maybe a larger diagram. I just add something, and it's hidden on top of it. Okay, and later on we'll see that some of the P2P technologies actually behave in such a way that they cannot be discovered, like Freenet. Okay, and so the other can easily be discovered. I mean, anonymity. You don't know who is communicating with who. Okay, so therefore, the P2P technologies use the concept of an overlay network on top, of course, of hiding information inside an existing message. So, therefore, what do we mean, therefore, network? So, we are saying now that peer-to-peer network, okay, distributed architecture, okay, that is composed of resources such as processing power, disk storage, network bandwidth, and so forth, okay? But without the need of a central coordination. Oh, no, let me use something else. Without the need of central coordination instances. And this central coordination, we are talking about it in terms of servers. So now, the beauty of this, just to recap what I mentioned earlier on, remember, they still have this processing power, they have disk storage, they have related bandwidth network, and hence they are as powerful. Directly over the net, here we can share anything in digital format. Look, we have eDonkey, among the many. In fact, I'm sure you have used several of these before. We will later on discuss some of these capabilities as such as one example that we'll discuss that they have used that in fact can be utilized for small businesses. Companies that cannot be able to invest but to utilize some of these. We'll look at some of these solutions. So instead of you trying as maybe as an SME to invest on servers, to invest on maybe client machines, you can just simply be able to tap into the P2P technologies. So how are they structured? So the P2P technologies come in two ways. We have what we refer to as structured and unstructured. Structured simply means that the overlay connections are fixed, and they use a distributed hash table for indexing. So remember, hash tables allow us to key value pairs. So if I'm looking for pair A, okay, I just need a key and it will me to that particular pair. So that means now that's structured. And in some cases it can be useful. In some cases it has limitations. So a structured P2P technology has connections is on in the overlay are fixed. Look at it like the way we can do circuit switching. So we are saying those circuits are fixed, and hence the communication follows a particular link line. And that means we have now a distributed hash table, DHT, which allows us for indexing purposes to be able to, let's look at it this way, that is robust. It has discovered where the peers are, and the moment you look at it, the moment you get to that hash table, you can be able to access that directly using a particular fixed connection. Okay? And then the other one is what we refer to as unstructured. So no algorithm for organization or optimization. Connections are arbitrary, okay? They set on the go. Centralized server is used for indexing purposes. So, for example, BitTorrent uses this, okay? And it has some central kind of server. We can also have a hybrid. So, okay, so basically in this unstructured, we have those ones that are centralized, okay, like BitTorrent. We have those ones that are hybrid, so which is centralized and distributed. For example, two groups of clients, maybe client and overlay. Kazaa is one of them, and those ones that are pure. Okay, pure simply means equipotent peers. Equipotent peers, meaning that they have the same capability. No peer is looking at the other as a server. Okay, so they have equal capability. All peers have equal computing power. Gnutella and Freenet are examples of these ones. Okay, so unstructured, if you look at them, they can be centralized, they can be a hybrid, and they can be pure. Examples of unstructured. So that structured, just to look at it before we maybe consider some questions. The structured example, okay, of P2P technologies, as I mentioned, we have a distributed hash table to be able to help us in terms of connection linkages. They have a global consistent protocol. Any node can be efficiently route whatever. Okay, and so the DHT basically will help in participating a key with a file which is new or to be accessed by the different whoever that is trying to request that particular file. So you can see if my net, I have keys that can use an algorithm, a hash function, okay, as an algorithm. The class it uses these examples of algorithms to help you to be able to identify or be able to access those particular files. On the other hand, unstructured network, like we said, is established arbitrarily. Okay, so this one here, just built on top of the telecommunication network. When a peer wants a particular file, it will just flood, okay, the network. Just floods the network. And as many peers as possible will share that information. And this flooding can create a lot of amount of signal traffic. So if we are looking at this later on, maybe, for example, some of the questions one will say, okay, what will be the advantage of someone thinking of using adopting P2P technologies. You can see this, especially if they're unstructured, we can simply generate a lot of amount. You can see of trust. Of course, there's no guarantee the file will be found, especially if we have very poor search efficiency. Because remember, it's being you're flooding that particular network. So most popular, and of course there are certain advantages. We look at them later on why this is popular. But most of the popular P2P networks are structured, okay, and where the links are established arbitrarily. And if you think about it, it is another way of simply saying it becomes very difficult to trace. Because if it's structured, I can easily be able to trace which clients were coming from where and what were they interested, particular file somewhere. Is it some file you are trying? Maybe there's a trying to have banned some of this software. I remember in one country where because it was being used to be able to share files, appropriate content. Okay, and so you notice because it was unstructured, sometimes it could be very difficult for you to be able to discover. So it had to the authorities had to use very skilled techniques to be able to identify some of those. So that's why it has been in some cases discouraged. Okay, so now we end up now with our P2P architecture, whereby all nodes are both clients and server. They provide and consume information, and they can initiate, and there's no centralized source. These ones here, so you can see now they're all just called nodes. Okay, so spreading or even sharing resources. So if you look at it just from a point of cumulative power, you see these ones can help you a lot in terms of trying to perform certain technologies, perform certain tasks, sorry. So now, when we look at those technologies, one of the first things that comes to mind is topology. How do we organize these topologies in terms of the way we can be able to derive use? So we have several topologies. So let's start with centralized. Now, the centralized topology, you can see, centralized comes from the point where we have a location that is there for administration. Okay, so if I one look start, so this ones here are just peers. Okay, sorry. This have here, they are just peers like the others, but the management is done there. Coherent, yes, all information in one place. Okay, so it's all the information in one place there. Okay, and then extensible, no. What we are saying, for you to add this, remember, we have to connect them. Okay, so that means that centralized, and whenever you add something on a centralized resource, you have provided for competition. So extensible, no. Or you can, but you end up having problems in terms of how services are provided. So that's why we use the concept of no. Fault tolerance, no. Because fault tolerance means if something fails, I can be able to do it elsewhere. Okay, so this means that if now, in our case here, if now our centralized location fails, yeah, it's a single point of failure. Secure, yes, I can simply secure one host that is handling all that. Lawsuit proof, easy to shut this one down. Because, for example, if I discover that the server that is controlling this, I can go and shut that. So lawsuit proof. Scalable, that's a problem, one machine. But in practice, of course, we'll see later on, we can have some redundant aspect. But so the question, there's a question on scalability. That question mark is simply saying, yes, it's possible, yes, but it comes with a few technical issues there. The second one is, okay, a ring. So you notice, okay, so we have a ring. So basically they are connected. Okay, so you can see that ring. Yeah, manageable, single rules of relationships. Yeah, because they're in a ring. Coherent, yes, easy logic to state because they're connected on that particular ring. So they have certain protocols that are understandable. Extensible, only one ring owner can add. Okay, fault tolerant, fail over to the next. So this fault tolerant here is good in the sense that if, for example, okay, if for example we have this particular host, if it fails, okay, another host can take over, another one can take over, and so forth. So fault tolerant, we can move to the next one. Secure, as long as you secure the ring who has an owner, that's fine. Lawsuit proof, okay. Shut down owner, did you shut the whole thing down? Scalable, just add one more host, and so that means that it can be scalable. Okay, now then another topology will be where we are looking at this in hierarchical fashion. Okay, hierarchical fashion. So we have that, which is connected maybe to that, which is connected to many others. Okay, so manageable. You see, we have a half there, chain of authority. So I need to be able to talk to the other hierarchy. So the direction can vary, okay? So the message that is coming maybe in this direction might be slower compared to another direction or vice versa. So that's easy. Coherence means if I have a file, sorry, as to demonstrate that. Coherence means if I have a file here, do I have the same file here? Or maybe let me put the, okay? So we are saying half consistency, half cache consistency. That means that some of the caches have the latest information. Some of the other caches will take time before they have that latest information. So cache consistency is not full. Extensible, yes, I can add more leaves. I can even rebalance the leaves. Fault tolerant, half. Root is vulnerable. Remember, that's the root. Remember, hierarchical. We start from one location. Okay, so in this case, the hierarchy starts at this point. Okay, here. Okay. Here. So how that can work because of it has been disabled, but it's too easy to spoof links, okay, because hierarchical is hierarchical. So some of those links can easily be manipulated, okay. Lawsuit proof, just shut down the root. Scalable, hugely scalable. Like the DNS, basically a distributed naming system handles this well. Now, another topology. So we're just looking at some of the topologies that are applied. Okay, so we have the other topology here is decentralized. Now notice, so we have that. You see, they are really connected. They are connected in many different locations. Manageable, very difficult. How many owners? Okay, so several owners. Coherent, difficult, unreliable peers. Now, there's one of the problems of having peer-to-peer technologies is that you don't have control of who the owners are. I just plug in. I can bring in a lot of things that might not be acceptable, but I'm still connected. So Coherence means I can even be lying that I'm handling cache consistency. Because part of what a distributed environment should be having is that we agree on cache consistency terms. You update a file, I update the file, so that if there's anyone trying to access that file from me, they have the latest compilable peers. Okay, extensible, yes, of course, anyone can join. Tolerance, yes, redundancy. So this one here might be doing this one, doing the same services as that one. I can be able to get a file that done maybe around here. Okay, so that means that there's redundancy. Secure, difficult. Okay, so but it's a research that is being done also there. Difficult because if you try to secure, okay, if you try to secure maybe this one, what about this one here? Okay, it's still connected to all the others. Okay, like in this case here, we have a scenario where this one is connected to here, it's connected to here, it's connected to that. So we still have those connections going on. So whatever you are trying to prevent will still not be possible. Lawsuit proof, no one to sue. Whom are you going to sue in this scenario here? Okay, because there are several that are connected, so it becomes very difficult for you to sue. Scalable, in theory, yes. Practice, difficult. Okay, because if the more you decentralize, you're adding more and more nodes. Okay, and so it can become also unwieldy. It can become so large in some of the scenarios. Okay, and so it's not very much scalable. But there are techniques that can be used, as we'll be looking at them later on. Then, of course, from what we have discussed, we can now combine some of this. We can simply say, okay, let me have a centralized and a ring. So now if you think about what we mentioned earlier on, we had some of those. So the capabilities of the ring are still there. But now we now have a scenario where we now have the nodes. Okay, so the problem, remember the ring had some very nice advantages. Okay, and now we are now having each one now can now be connected to another set. So they can also form several rings that are involved there. So you end up now saying that in terms of this, manageable, just manage the ring, coherent as the ring, okay, extensible, no more than the ring. So we can extend, but as long as the ring brings the what I call the limiting factors. So if it's bigger, then we have capability. Consider it, for example, if we have a ring surrounding maybe Nairobi, then we have potential to connect maybe other related maybe counties very nicely. Okay, but if it's a smaller ring, we have problems that can cause some bottlenecks. Fault tolerant ring is huge. Okay, so it's a win. Secure, you are secure the win. Single place to shut down. So you just go for the ring and hence you shut it down. Scalable ring is a huge win because you can simply be able to utilize that capability. Okay, like I said, the larger the ring and the number of nodes, the better it is in terms of trying to access more. And one of the other combinations that we can now have also is where we have centralized and decentralized, centralized plus decentralized. So we have this one here. So centralized, and so this you can see this is an example of a centralized, okay, that is also centralized. So we have this one here is our central location, but we have also these related smaller peers. So it's a combination. Okay, so here we end up now manageable, same as decentralized, coherent, better than decentralized. Okay, and extensible, anyone can still join in, and then fault tolerant, plenty of redundancy, which is a good thing, and secure, same as centralized. The moment I secure centralized, the same secure. So the same problems that we have in decentralized, and then lawsuit proof, still no one can sue because there are many different peers. And then scalable, this looks very hopeful because we simply need to have centralized, and then we move further and further, and then we have accessibility. So therefore, before we evaluate, we look at questions. These topologies, therefore, have caused a lot of problems for politicians. I mean, I look at in terms of government and legal. Okay, one of the bigger issues that comes in: how hard is it to shut it down? Okay, can be good or bad. Yeah, and that's why, remember, I gave an example of one country that had to shut down Kazaa because people were sharing inappropriate files. Okay, and so in that case, you have to know, and that's why they most of the time is to trace what, where, okay, where is this? And you remember even recently where we had blockchain, okay, an example where they had to trace one individual. I don't remember one of the Asian countries where they had to trace and find that particular individual. So it has to be traced, and then which is sometimes illegal, because sometimes some of the things you consider being illegal, some people might consider being illegal. So that's why you can see there's a lot of issues that are related to this. Security, okay, issue is about how hard is it to subvert, because when you are looking at it from a security point of view, you're saying most how point how much some of the services being subverted by some of these peers. Okay, and then of scalability, we're saying how big can it grow. So some of these things we are going to discuss in detail as we go on. But now I think it's time for us to be able to maybe field a few questions so that we can pick up maybe something that was not clear. As the others maybe are thinking of the question, there's a question that was asked: what is the difference? Both these two, okay, these two are nearly the same. One leads to the other. Okay, if something is robust, it means it offers fault tolerance. What do I mean? Robust. I'll give an example. If I have a servers, if I have only one server, if it fails, then my services can stop. But if I have more than one server, one fails, automatically it takes me to the other server. And that means that that system is robust, and therefore it provides fault tolerance. Fault tolerance means if you have any problem, your services will not stop. Your services will still continue. So that's why we have fault tolerance techniques to handle what we call as redundancies. So I have more than one server. Okay, like Google, we have more than one Gmail server. So that is robustness. That is redundancy, which means that they have considered being fault tolerant. And that means users can be maintained, can simply be able to get that robustness. So it fails and still transfers you directly to another. And the concept of Victor is asking, what's meant in unstructured? Okay, now we say it unstructured. Okay, so maybe let me go back to that point. Okay, I don't know. Maybe, okay. All peers have equal amount of power. Okay. Now I get what you're saying. So we are saying in that regard, we are saying that they have enough, the same computing power. Okay, so and let me use the example. If you have a laptop, let's say with 4 GB hertz in terms of RAM, okay, and someone else has the same, okay. So we are saying that they have enough computing power such that each one of them can contribute cumulatively. This one contributes 4 GB, another one 4 GB, another one 4 GB. That is what I mean by power. So the power here, I mean, you should look at it in terms of capability to perform tasks. Distributed hash tables, okay? So the distributed hash tables, okay? If I go back to that slide there, distributed hash tables, what I mentioned here is the distributed hash table is the algorithm, okay? So an algorithm that can be used to route messages. So, routing messages across the network, I need to be able to know the destination. From source to destination, I need to be able to know where that particular location I'm going. So that is a routing. Now, so the distributed hash table, okay, gives us an opportunity for us not waste time trying to route. So it will go. Notice if I use the diagram here. So that is your cloud or your network. I have a key, and this is the hash function. It will lead us to the forks as a file. Distributed hash table is the one that performs the indexing. I'm looking for forks. I have a key to that. The moment I get that particular key, it will lead me to the source of the file forks. It will lead me to the source of the file, like for example, the red fox walks across the ice. So the distributed hash table is just useful in terms of routing. And it is made easy because moment you have a key, it can tell you where that particular file is, or all the peers that are storing that particular file. Okay, so the other question okay, ring topology. Okay, so the ring topology, so where is my ring topology? Okay, so I have that. So let me, I've brought it back. So ring topology, yeah. So we have this. So this node is connected to that. This is connected to this one. This connected to this. This connected to that. This connected to that, and back to the same location. So we end up having that they're all connected through that particular network. So we end up having that particular ring. So they're all connected. Okay. So if you look at that, we are saying that if I start here, I can go around and come back to the same location. And that's why you can see the advantages, simple rules, because in a ring topology, we expect that they have agreeable protocols, okay? Easy logic for the particular state because they are working together. And of course, a ring is owned by one particular person or one particular individual. Only ring owner can add to be able, so you are admitted to that particular ring, okay? And of course, if something fails, you take over. You can easily put to the next. So if this one fails, you can hand over to the next one. So I'm just trying to go whichever direction. Remember, you can use the other part. But usually you use the shortest path in terms of how we utilize that in routing. Okay, so Let me see. Okay. So, John, you're asking what updates the distributed hash table when a new node joins the P2P network? Now, remember, we have what we mentioned earlier on in terms of discovery. The network uses the concept of discovery. So the moment I plug in a new node, the packets that are being sent will discover a new node has come up. Okay? And so the moment that is discovered, that information can be updated on the distributed hash table. So that is basically it has been discovered. And when you disappear, of course, that can be eliminated. Okay, and so that is robustness. So we keep on discovering. So that's the beauty of this. So when you join, you are discovered. You can overview your services and you can leave. And then, of course, the routing table will be updated and your information will no longer be there. Okay, I'm wondering what happens if a node in a ring is isolated. I don't know what you mean by isolated. Do you mean disconnected? Because, okay, let me try to use, maybe let me assume something here. Supposing, for example, what you're saying, this one here, okay? Supposing it's cut there. Okay, supposing, yes, disconnected. Now, notice if this is disconnected, okay, that, let me assume I have cut it in that location, okay? So what is going to be reached? I can go this way, okay? I can go this way and still I can reach it. That's the beauty of the ring because you can use either direction. Naturally, if it was not disconnected, I will use this one, okay? And this direction, I'll go like that. But if it is disconnected, then I use the other part. And that's the beauty of a ring because, yeah, you are simply say you can go whichever direction that you have, whichever direction to access your next neighbor. Okay, yes. Okay, so let me look at slide 10. 10, what did I have on slide 10? I don't know if I'm not getting what you're saying. What do you mean by mapping? Don't seem to get what you're saying there. Explain the final point mapping in slide 10. Oh, okay. Let me, yeah. Now I get, so you are maintaining mapping, okay? Here. So mapping basically means maintaining keys, the data. Keys, because the key will lead you to the data. So these are handled by nodes when there's a change in the amount of participants causing minimal amount. Remember, a file can be stored by several, okay? So that means that the hash table is robust enough to be able to say this file is, that's what we call mapping. Because when you identify the key, it should be able to lead you to different, to lead you to those that have this particular file. And so that's what we mean by mapping. So it has to be maintained such that now, when that particular file, one is interested in that particular file, then they can be able to access it. So it has to be robust. So if you change a file from one location to another, the key will be changed. That's what we call mapping in that regard. Now, let me maybe, the last question, and I think we take a break, extensible and scalable. Okay, now scalable, let me start with the scalable. Scalable means that basically it can grow in terms of scale. Okay, so I can add, I can be able to reach a wider location. And that's why I wanted to use geographical. Extensible means that does it have the capability to scale? So extensible is more towards what are the equipment you have in place such that it can grow. So if I have more servers, I can say that thing is extensible, yeah, because I can add more users. Hence, it can be scaled. So the two are related, but extensible is more about what you are using to be able to ensure it grows. So I might want to scale something, but it might not be extensible because I don't have enough nodes. I don't have enough servers. I don't have enough, the network is not strong enough. So extensible relates to the power maybe in terms of the network, in terms of servers and so forth. So extensibility is the one that supports the concept of being scalable. Okay, so I think Sam, let's take a short break, and maybe when we come back after the break, we can now be able to explore a few things related to what we have discussed. Maybe 5 minutes will be good. Please maybe take a cup of water or something, relax a bit, maybe stretch a bit, take your eyes off the computer so that you don't have fatigue. Okay, so 5 minutes, please. Again, okay, so are you back? Okay, so let's start again. So now we have discussed several things. Some of them now become very easy to explain now. Okay, and so let's start basically now things like this ones here. So P2P2 computing. So now we have several things now. Computing. So the advantages. Okay, so the nodes are part of the system. The more demand increases, the total capacity of the system also increases. So we can increase demand, we can increase capacity, we can increase that P2P structure. In contrast, if we're using a network client-server architecture, we have limitations. Okay, as you add, the system resources decrease because the resources are fixed. In the first case, you remember, I think the question that was asked earlier can help us here. Remember, we had the computing power. So each node that you add adds the computing power, which is a good thing. Of course, no single point of failure due to robustness of the system. All clients provide to the system. Okay, so that is a very good thing about P2P technologies. Let's refine that. No central point of failure. Okay, for example, we have here no central point of failure. For example, the internet. We do not have a central point of failure because we have several servers. Okay, handling this. Of course, if the file is not stored in multiple locations, okay, because I might have a restricted file, then you might feel, oh, yeah, I have that restriction. Yeah, but we are saying that the file can be stored in several locations. So this is no central point of failure. Scalability, yeah, of course, we can add more peers to the system and scale to larger networks. Okay, and so remember, the point we talked earlier on the last slide that each new computer
each new node you add comes with power, computing power. Okay, so we add more peers. That means that it's now extensible. It can expand. So applications, of course, we can share files. We can process share. Okay, process sharing in two ways, where we are looking at it in terms of tasks that are being performed. Okay, and also we can look at it in terms of the middleware, the services that are there that are across the entire set. And then, of course, collaborative environment. We can work together because we have the potential to be able to use those capabilities that are available. Of course, it comes with disadvantages too. Okay, so we cannot forget about that. So disadvantage. How do you keep global state, consistent? Now, this concept here is loaded, but I will try to explain, but we'll handle it later on. Global state consistent. We are saying if I have file A stored by several peers, is it the same file, or does the file have exactly same information? Capacity in terms of, let's say, MB, in terms of what you have written on that file, is it exactly the same? That's what we mean global state consistent. So is it the same everywhere? So making this happen is a problem, because what happens, you change a file, okay, and you have no central coordinator to say, can you all update the file, or can you all reject the file and get the new file? Okay, can you all maybe throw away that file, the new file? The next one, distributed coherence protocols. Coherence is coherent protocols are protocols that enforce consistency. Those are protocols that say, if we all have file A, it can tell us, can you all change this file in this particular way? Or have reject and then keep this particular copy. So it enforces consistency. Nodes are not created equal. Yeah. So we say they come with computing power, but your laptop might be the latest, mine might, so capabilities might be a problem, might differ. So the same server capabilities as yours. Okay. DT. Okay. Programmability is possible for us to be able to program those behave in the same way. Okay, so it same. Maybe you have a ring. We have an owner who has some ways that they're doing it. They're handling. They have different protocols among that ring, which is different from mine. So in that case, therefore, we have different ways, and that's why we are comparing. So here we are comparing these to decentralized coordination, which will vary from one to another. Then we have another set of disadvantages, of course, security. Okay, this one comes without saying much. Security is a concern. The moment I'm connected, I have opened my house to anyone. Okay, so attackers may use the first or can attempt to control all other nodes, which means that we have a heavy bandwidth usage. Of course, there are those companies that P2P, like for example, any company that has, let's assume I'm an aspiring musician and I have my nice music that I have and I upload on one file. Of course, if you start downloading, I might not be able to get royalties and income from that. So if I have a promoter, they will be unhappy with this. Okay, so they might use fake junks maybe sometimes on the shared files. So they corrupt some of the files that they become useless.
okay, or download or something like that, to ensure that they affect the whole process. All the traffic to affect it, and of course, potential some of the people were sharing inappropriate files. So that is an immoral issue, okay? Of course, it has several dimensions, but that's an immoral issue. So potential legal. So if you are found with that particular file in a certain country, you might be sued for that. In another country, you might not be. So we have those potential legal and illegal and moral concerns that can accrue because of the files that are being shared. And that's why it's very sensitive. P2P technologies have those kind of, brings those sensitivities. So here, this is something I just picked up. In fact, one of the files I've shared with you online, on e-learning. So examples of some of the problems that are there that you can accrue, you can have poisoning attacks, providing files whose content is different from the description you are getting. This file is different. And you have seen one example is, I'm sure you have tried to download, find someone will give you, go to this particular link. You go there, you're looking for is not the correct one. Polluting attacks. So we have bad checksums, bad chunks added to that. Protection attacks, users or software make use of the network without contributing resources. Okay. Remember, we wanted to use combine the resources, and then of course they can also insert viruses in the carried data. So when you download that file, you have malware. Okay, and because you are interested in that particular file, if you're not careful and your system is not well served, you will end up downloading. So we have issues of malware. Okay. Structure. Filtering. Network operators may attempt to prevent peer-to-peer network before data being carried. Okay. Identity attacks, tracking users on the network for harassing or legally attacking maybe them. Okay, so some of the possibilities, and of course, spamming. So unsolicited information comes because you are connected. So those ones are just things I'm sure you can easily be able to look at quickly. But some of the advantages, of course, like we mentioned. So of course, things are available. Okay, if something is open source, for example, let's assume I'm so generous, I have my nice music, and then I say it is available. Let me redundancy. Okay, and of course, some of these we have Napster, Newtel, Freenet, and Kazaa. So we this part here, okay, we're going to look at in detail how each one has been designed and maybe part of the topology that is used. So for now, I'm just mentioning, but we'll look at them in detail. Then, okay, of course, in sharing applications, so large-scale computations. So if I have something that I want to compute and I don't have enough processing power, I can be able to have that in different locations. So we have this computing, large-scale computations can be done. We can do data analysis, data mining, scientific computing. And so these some of these capabilities we can have on distributed net, worldwide computer, and so forth. Okay, and remember, P2P technologies are running on top of the World Wide Web. Okay, so yeah, basically we are still the same. Some of the capabilities we talked about in terms of the client server model are some that we also have here. In terms of collaborative applications, so the previous one was about sharing applications. Okay, so if we look at collaborative applications, we have several. So real time, like for example, I'm sure we are right now on Zoom. Okay, so a real time application. Okay, so we have instant messaging, virtual meetings, shared whiteboard. Yahoo, no, including Zoom, Microsoft Teams, and so forth. So those are collaborative applications that have this capability of peer-to-peer. And remember, the way we are looking at it, like Zoom that you are using right now, we is peer-to-peer. So if I give you the rights to be able to share, you can be able to share and be able to present. So that's sharing collaborations. Of course, there are technical challenges. Okay, peer. How do you identify which peer is where? Routing protocols. How do you know how to route? So we gave an example of distributed hash tables, but of course there are issues there. Okay, we also can have network topologies. Okay, so we have talked about those ones. How do you discover which peers are coming in? Okay, we have issues to do with communication and coordination protocols to make sure that it works well. It becomes very difficult to gauge, okay, to be able to gauge the quality of service. How do you know, okay? Because quality of service has certain parameters. Okay, you can be able to say, for me to have attained certain quality, these are the parameters. Okay, so that is a problem. Security, of course, without explaining much. Fine-grained resource management. Fine-grained means that I know I can be able to tell you in detail to perform a certain task. And that happens if I have control of that particular node. Okay, so like if I have a server, I can easily be able to say, these are the fine-grained resources that you can do. But a peer just connected, it has its own maybe protocols, it has its own maybe control powers. So I cannot be able to control that much. Okay, so that is a problem to that. So we might, as part of our discussion, we'll look at some of the solutions to some of these, how to handle it. But let's go back in history a bit. To see the growth of this, let's go back in history. So I will, let me start, can see from there, 1993. Okay, so if you look at that, from that point, yeah, okay, we have, and this data is up to 2006. So you notice from here, we had at that moment, at that time, 1994 there, you can see FTPs were very high, popular. Okay, so 1997, you can see web was growing, and by 2000, you can see it was a lot. Then you can see P2P technologies around 2000, 2001. So we'll see, in fact, where Kazaa and the rest started was around 2001. And so you can see the popularity. So by 2006, okay, you can see by 2006, you can see how P2P technologies are there. Of course, you have also the web there, P2P, email, and the rest you can see. So you notice, therefore, that at this moment, as we are growing, you can imagine the popularity of P2P, okay? P2P technologies. Now you can see we are actually having our discussion using P2P example of application. So the percentage of use. So it has become very popular. Okay, it has become popular over time in terms of usage, and the uses are with the time. You can see we have a lot of uses that are very, very, very novel. So that system. So okay, so from that diagram, you can see the figure I had earlier on, basically something like Napster around 1998. Okay, so that's when the concept was there. And basically the point was to share resources and services by direct exchange of systems. Okay, and so the peer can decide the data on their computer, okay, what the data is on their computer, and what can be shared. Okay, parties have the same capabilities as we said, but the concept here now, we are looking at them as servant. That was the concept of Napster, servant. It's a server and is a client at the same time. Okay, so this is another concept. So instead of using the term that was clear, server, so we are saying servant. So it's also a client and is also a server. Okay, so that takes us back to some of that beginnings of that. Then we have okay, so the types of peer-to-peer system. We have mentioned some of this, but let's try to refine this when we are looking at particular ones. Okay, so the originally we are just saying centralized, decentralized, but out examples of where each of these maybe topology and the way the overlay network is structured and where it's applied. So centralized, okay, where information of all peers, okay, and then decentralized. So Napster, okay, is that example. Decentralized, we have several, of course. We also in decentralized, we can have them as structured, and then of course we can have them as unstructured at the top here, unstructured. So in terms of those that are unstructured, so do not follow in a structured way. Remember, in a structured, the nodes are arbitrary. We do not optimize the algorithm. Okay, we can simply be able to flood. Okay, we can simply be able to flood that particular network. Okay, and then which can cause network congestion. So the examples that we have these two here. Okay, of course there are others. This is not the final. So we have Gnutella and Gaza as examples of those that are unstructured. They are decentralized and unstructured. In terms of the structured, okay, we have those that are code and pass-through, among others. So structured, so remember this part here. They have an algorithm, okay, that is used particular algorithm, and Freenet, code, and pass-through are examples, among others. I'm sure you can, as we discuss this more, you will find other ways. Part of that algorithm is structured if you add more. Okay, so I think for today I want just to talk about Napster, how it works. Then we stop there so that we have enough time to maybe field questions and maybe some chit chat before we call it a day today. So Napster, therefore, okay, of course, one of the most important thing was the interest at that particular time was sharing of music files. Okay, so that's the whole. That's how it all started. So I can upload some file onto the server, and then you can have a search request. And the moment I have that particular file, I can connect directly to that and be able to get that information. So if I go to the diagram, I'm simply saying that this node here is your computer. This node here is the one that has a particular file. And we have this, okay? This is your central index server. Remember, indexing to be able to help you identify where that particular file is. And you can see the way it's connected. Okay, sorry, I think I needed to use an arrow. You can see the way it's connected, okay, to all these particular nodes. Okay, so now this your computer here, yeah, which is down here, identifies it needs a particular file. Therefore, after that, it will be able to ask that one, which has index 7. You discover the file is there. And therefore, after that, what will happen next is that the two computers will now be able to interact and be able to share that information. So the central server has done its work, and therefore the two can be able to continue. Now, so from what we have from there, therefore, we end up saying that NAPSA central server, so it has a single point of failure, prone to denial of service, and ensure correct results. Okay, so denial of service, we know where the server is, we can hit it. Okay, single point of failure, if that server goes down, we're in problem. Of course, we know, we'll talk about ways this can be solved. Okay, but that's the whole point. Search is centralized. So, and remember in the previous diagram, we had to search in a central location. Okay, and then it has a routing algorithm. It has, it has indexing to be able to find those particular files. And then, of course, search is centralized. And then after that, direct, peer-to-peer. Okay, I think I've been talking a lot. I want us to get to questions. In our next class, we look at some of the P2P technologies. Feel free to read more, and then I'll be glad if we share more. So, time for questions. Okay, so okay. Central point of failure. Point. So there's basically the same thing. So they maybe looks like a difference in terminology, but it's basically the same. Okay. These recordings with the okay. So the module leaders were here. In case I forget, then I can talk to and discuss send me uploaded. So the moment I have it, I can be able to upload because it's automatically recorded. So I can easily be able to find that, and then I can have it on e-learning platform. Okay. Now, we have some minutes here, but I just wanted to pick up just a few things. Some of the things that I wanted to just talk about. So I've posted a tutorial, and when looking at it, because I gave a deadline of I think 6, but when I was putting at it, because I was here and there. So if you look at it, it has some extension there. But please, to make sure that, because you notice some terms now, I'm reusing them, things like single point of failure and so forth. So it's always good to work on that so that we can see how to move, because the terminologies keep on increasing. The other one is, I am open to, supposing, for example, one of you is interested to have maybe something that is burning, something that you just want to discuss, even outside the particular course. We can agree if we set up maybe even a Zoom, we can chat. Okay, maybe we can chat and see how we can handle some of those. Some of the questions that I've put, as much as I will not be focusing on trying to give specific solutions, but I am open to people trying to, I'm open to just trying to clarify a few things. So again, if you want, maybe in our next class, you say, okay, there's this thing that was there, maybe just clarify. I'm not giving a solution, but I can just give a few pointers. I'm there. Yeah. So that's part of what I should be able to do. So I'll be glad if someone is maybe asking to stop. To be able to expound some of that. Okay. The other thing is about some of those things I'm sharing. Okay, I was trying to explore, and I think I'll be in the university tomorrow because I had given some assignment one of you. So because we have a large class, okay, the class is big, so I wouldn't want to have most of the emails coming to me. So one of the things that I might want to see if I can put that information on that information coming to e-learning. So I'll investigate that so that you can upload. So basically, it means that I saw, I think on Tuesday, yesterday, okay, I checked and only 88 of you had registered on e-learning. Please take your time and register so that you have things there, so that I can have a central location. I can be able to, when I decide to collect the assignment, I collect it once. When I decide to pick a few things, I can be able to do it once. So many, I might lose it. I don't think that is the right thing to do. Yeah. So I think it's important that you do that. Now, someone is asking a question here about throttling. Throttle is basically something that stops, something that affects. Okay, so it means that if you are trying to throttle the higher speed traffic, you are simply saying you are trying to prevent. Let's look at it. It comes from even the concept of mechanical machines. So I'm simply impacting on the service that can be provided. Instead of having a seamless traffic, I'm impacting on that traffic. Okay, so it might go smoothly the way it's expected. Okay, so so far, I don't know if someone has any question there or anything. Someone wants, if you want to talk to me, send me a private where we can talk about it. We can chat after this. But otherwise, I think so far, I'm hoping things are fine, but that's just my hope. Feel free to say, oh, no, I'm having a problem here in terms of maybe some of the things that we have. I'm here for you, okay? And that is good. So that basically at the end, it's important that when you fill the course, you have, apart from understanding, you can be able to apply. So I am there for you to be able to, whichever way we want to look at it. I'm glad. I'll be glad to help. Whichever. So next week on Monday. Okay. So please remember to update your information on your student attendance list with your module leaders. And in case it's shut down before, because we are looking at consistency, to write me a mail. I don't think that's a big issue because it will just be a few isolated mails. Because maybe something happened, maybe something happened along the way, and so you want to get back to me. I'm open to it. Attendance should not be any problem in this regard. Okay, thank you very much, and it was a pleasure to have a good. Afternoon.